Yeah. Thank you for the introduction. Hello, everyone. So I'm going to start with some um, very unpleasant images of natural disasters or maybe bomb explosions or things that could end up collapsing buildings. And one of the main problems in cases like this would be how can we get to the survivors that might be under the rubble, and how can we identify them and find them and rescue them on time. So there's different techniques. Dogs are always great detectors, but there's also a lot of efforts by robotics groups to develop robots that can identify survivors under the rubble. For example, this is a group at University of Denver I'm working with. They make these crawling robots that can crawl under the rubble. They can pass through narrow spaces that is hard for humans to get access to, and trying to find out if there is anybody or any animals down there trapped to be rescued. So I was talking to them, and they were interested in having one of the sensors they would like to have is a CO2 sensor on this robot, a very small size, low power CO2 sensor to be able to detect survivors. Because if there's somebody there breathing, there is going to be a high concentration of CO2 in that limited space. So that's a good way of detecting people. So how do we make a CO2 sensor? Well, I believe there's different techniques, but I've been working on resonators over the past more than 10 years. So that's pretty much the only thing I can do. So how do we make any problem I see, I try to solve it somehow with a resonator. How do we make a CO2 sensor using a resonator? The concept is pretty simple. If you can somehow absorb the CO2 onto the sensor, the added mass could change the resonance frequency. Just the same concept as, of course, crystal microbalances. When you get molecules absorbed, the increased mass gives you a shift in the frequency, and by measuring that shift, you can tell whether or not you have that specific agent in the environment. Um, so the key is to cover the resonator surface with a very thin layer of some selectively absorbing material. Now, this is the type of resonators we've been working on over the last few years. These are thermally actuated resonators. They use thermal actuation and piezoresistive sensing. You can see the mode shape here from different angles. Basically, this is the most common structure we use. There's two plates attached to each other with these narrow beams in the middle. We actuate them by passing a current between these 2 points, between this end of the resonator and this end. And because of this region is the narrowest, you get most of the heat generation in that region because of the higher ohmic loss, because of the higher electrical resistance. So because of the periodic thermal expansion and contraction, you can get uh, these resonators to operate in this in-plane mode. And since it's an in-plane mode, it can give you relatively high quality factors, a few thousand in the air. And there's no small capacitive gaps that usually reduce the quality factor in air. So they can easily operate in air. The power consumption is usually a concern for these devices, but that could be reduced down to sub-milliwatts pretty easily. The key is that to have very narrow actuator beams. Um, a little more on the operation of these devices. One of the things about thermal actuation is that people usually think of it as a very slow process because it generally takes things time to warm up. Here you can see, for example, an example of a thermally actuated resonator resonance structure. And what you see is the heat distribution. As the current goes up, you can see the heat wave kind of getting generated in the narrower area and then dissipating as the current goes down. So here we have interactions between thermal, mechanical, and electrical domains. The thermal domain is more like a low pass, which is where the assumption of low speed comes from, because you have the heat capacity that needs to fill up and raise the temperature. But the key is that if you make the dimensions small enough, because there's a third order relationship between the thermal capacity and the dimensions, So if you shrink them down, you can get the sizes, you can get the heat capacity small enough to be able to actuate these at very high frequencies. We have actually shown thermally actuated devices that look like this, up to about 200 megahertz. So that frequency is not really an issue for thermal actuation. And then we have the mechanical structure, which is a spring mass system. In electrical domain, it would be an LCR. And finally, when you get the vibration going, you have a stress in the beams. So the same beams that are doing the actuation can be used for detection of the response using piezoresistive effect. Now, the great thing about these devices and the main reason we started working on them was the simplicity of fabrication. All you have to do is to take a SOI wafer, a silicon insulator, pattern the device layer, get rid of the underlying oxide by dipping it in hydrofluoric acid, and you are done. You have your suspended resonating structure, a single mask standard MEMS process that pretty much everyone can do. The next step in this case was to coat it with something that can absorb CO2. I'm not a chemist, but I've been talking to some chemists, and one of the first things they proposed was PEI, or polyethyleneimine, which is a polymer that has these amine groups hanging from it, if I'm not mistaken, and that can react with CO2 pretty well. It's more like an acid-base reaction. CO2 is kind of acidic, and then you have these amine groups which act like a base, and they can absorb CO2. So to coat the resonator, this was probably the most challenging step in the process, because these are really sensitive, tiny devices. If you look at the dimensions, it's about 50 microns across. So you have to do it in a way that you don't disrupt the operation of the device. So what we did was actually pretty simple. We just diluted the polymer in a solvent and spin coated onto the resonator. You can see that the surface is not flat enough, and it's a little too dark, but I can see here there is some residues underneath, but it's not big enough to disrupt the operation. So you can still get operation with a high quality factor with this coating on top. Then we did some measurements. We did a custom-made vacuum chamber, basically a plastic container with some holes for the gas to flow in. And you can see whenever CO2 comes in, you see a clear frequency shift. It's actually a pretty large frequency shift, over 1,000 ppm. And as soon as the CO2 source is removed, it goes back up. Now, it looks a little weird here. Usually you would expect a decaying exponential kind of decay when you have absorption of gases. I guess the reason it's showing that you are not limited by diffusion, and basically all the coating that you have reacts with CO2 pretty fast, and it gets saturated. I guess that's what it means. One of the other interesting points here is that when you change the current of the device, because to operate these devices you need to have a DC current for piezo-resistive actuation, and you also need to have an AC current. When you change that DC current, that changes the static temperature of the device. So we operated this at two different DC bias currents. At 6 milliamps, of course, the device is hotter, so its initial frequency is lower, because generally when you heat up a resonator, its structural material becomes softer, the frequency goes down. But also, if you look at how much frequency shift we get, it's a little less when you operate this at a higher temperature, which is kind of expected. If you heat up your surface, gas molecules are going to be less likely to be absorbed on the surface. So this was the CO2 measurement results, which was pretty promising. One of the problems, or it could actually be an advantage for the PEI coating that we use, is that it also absorbs water. So people actually use it to make humidity sensors as well. So we did some humidity measurement as well. Here's a test setup. We took a big bell jar and We didn't have a good humidity control system, so we just my students just heated up some water and put it under the bell jar while monitoring the humidity levels inside using a commercially available humidity sensor. And here you can see it. There's a clear frequency drop as the humidity, the relative humidity goes up. So this could be a bad thing because it could give you positive, false positives in the response. But it also could be a good thing because if you think about it, human breath has high levels of CO2. It also has high levels of water. So higher concentrations of water inside the confined environment under the rubble could mean a human survivor. Here's some cyclic measurement results for water absorption for different humidity levels. This is changing humidity from 29%, which is the background humidity, to 85. This is 29% to 51. You see a clear change in the amplitude of shift. So the last test we did was actually trying to measure the human breath. So we connected a mask to the chamber, and we had someone blow into the chamber, and you can see every time that the person blows, there's a pretty large frequency shift on the resonator. As soon as the breathing stops, it goes back up. So it can detect human breath. So in conclusion, we have demonstrated a CO2 sensor that is sensitive to both CO2 and humidity levels, and it could be potentially used for detection of survivors in a disaster area. And I'd be happy to answer any questions on this.